In this video, we simulate the fetching, decoding, and executing of the load and store instructions. For this purpose, we have built a simulation circuit in Circuitverse Simulator. This is the simulation part of the instruction code load and store and data instruction video of the How Computers Work Building Scott CPU YouTube playlist. The links to the playlist and to the circuit are in the description. In Scott CPU, as in many other kinds of CPUs, the ALU operates only with registers, so we need some kind of instructions to get data from the RAM and to store data into the RAM. Here we have built a simulation circuit to fetch, decode, and execute both the load and store instructions. This circuit can do just this. It cannot run other kind of instructions. I put here just the hardware needed to run the load and store instructions. Let's see a quick overview of the circuit. Here we have the timing blocks, so the block generator and the stepper. Here we use the timing blocks and the wires coming from the instruction register to give the enable and set pulses to the dedicated registers as the memory address register, the instruction address register, the instruction register, and the RAM. Here the logic to give the set and enable pulses to the four registers from R0 to R3. Here we have the instruction register and the logic to control the load and store instructions. Here the instruction address register. Here the RAM memory. Here the ALU, and these are the four registers of the Scott CPU from R0 to R3. Let's see more in detail the timing blocks, so the clock generator, which also generates clock enable and clock set, and the stepper. The stepper is composed by 6 steps lasting a clock period each. Scott CPU uses this stepper to give the right sequence to all the operations the CPU has to do. Moreover, I introduce a block called stepper cycle to decide how many stepper cycles we want to run. In this way, I can stop the simulation and see the result of a single instruction. Scott CPU operates an instruction per stepper cycle, so an instruction per 6 clock cycles. Of course, it is very inefficient, but Scott CPU has been created for educational purpose. Here we see on the left the generation of the pulses to bus 1 and the generation of the enable pulses to the instruction address register, to the RAM, and to the accumulator. On the right, we see the generation of the set pulses to the instruction address register, to the instruction register, to the memory address register, to the RAM, and to the accumulator. The pulses are created through two input AND gates, having as first input the clock E or the clock S, and as a second input the right step of the stepper, which makes sure the pulses are created at the right time. Here you see the instruction register. In Scott CPU, the instruction has 8 bits. If the first bit is at 0, we have an instruction different from the ALU instruction we have seen in past videos. The 3 bits from the second to the fourth tell us what kind of instruction we have. So for example, this instruction says load the content of RAM in RB register being the address in RA. In particular, in this case, the RAM cell address is in R1 and the register loaded is R2. So the opcode for the load instruction is 0000. The 5th and 6th bits define the register in which we have the address of the RAM cell from which we want to pick the data. We generically call it register A, which in this case is register 1. The 7th and the 8th bits are related to the register in which we want to load the data coming from RAM, generically called register B, in this case register 2. The Scott ALU operates only with the 4 registers from R0 to R3. So we need 3 decoders 2 to 4 to manage the 4 registers. In the blue ring we see the decoder to select the register A. We only give an enable pulse to register A to put a byte on the bus. In the red ring the 2 decoders for selecting register B. We give an enable pulse on the left and a set pulse on the right to acquire the result of the operation and put it in register B. The decoder selects the right register, but the right time for the pulses come from the clock enable and clock set along with the proper step. Here comes the step for the enable of reg B. the step for the enable of reg A, and eventually the step for the set of reg B, which is the last step, in which we store the result of the ALU operation in a register. Here the logic to implement the opcode of the load and store instructions. We have a 3 to 8 decoder which can control 8 instructions. The first two are the load and store instructions. The bit 0 of the instruction register is connected with these 3 input AND gates driving the opcode of the ALU. In the load and store instruction, this bit is 0, so it forces the ALU opcode to be 000. So, to select the header, we use in the fetching phase to increment the instruction address register by 1. Moreover, the bit 0 put a 1 in one of the input of this AND gate through the NOT gate, enabling them to receive the data from the decoder. If the bits 2 to 4 of the instruction register are 000, we have a load instruction and the first line of the decoder is high, creating the load signal. If the bits 2 to 4 of the instruction register are 001, we create the store signal. The store instruction could be this. It means store the data in R2 to RAM being the address in R1. Let's see in detail how to give the right sequence of set and enable pulses to move the data from the RAM to the registers. We imagine the load instruction is already in the instruction register, so it has been decoded, creating the load signal. When the fourth step arrives, we give an enable pulse to the register A to put the address of the RAM cell on the bus and a set pulse to the memory address register to acquire it. When the step 5 arrives, we give an enable pulse to RAM to put the content of the selected cell on the bus and a set pulse to register B to store it in the right register. So the load instruction needs only step 4 and step 5. Now, let's see the store instruction and how to give the right sequence of set and enable pulses to move the data from a register to the RAM. We imagine the store instruction is already in the instruction register, so it has been decoded, creating the store signal. When the fourth step arrives, we give an enable pulse to register A to put the address of the RAM cell on the bus and a set pulse to MAR to acquire it in the memory address register. When the step 5 arrives, we give an enable pulse to reg B to put the content on the bus and a set pulse to RAM to store it in the right cell. So the store instruction also needs only step 4 and step 5. Here you see the instruction address register connected with the bus in red. The IAR contains the address of the next instruction stored in RAM. This register is updated in the first 3 steps of the stepper cycle to point always the next instruction. Here you see the 4 registers from R0 to R3, so our reg A and reg B, selected by the last 4 bits of the instruction. Here you see the RAM having 2 inputs connected to the bus, one for the address connected to the memory address register and the other for the data. Here you see the ALU with 2 inputs connected to the bus. Input A is directly connected to the bus and input B is connected to an element called bus1, which puts the number 1 on the bus when we want to increment by 1 the instruction address register operation we do every stepper cycle. Bus 1 is then connected with a temporary register where we temporarily store one of the operand of the ALU while the other is on the bus. Eventually, we have the accumulator register where we store the result of the ALU operation before storing it into the selected register. So now we run a load simulation, so we simulate the load instruction. And for example, we can choose this instruction here, 0000. This is the opcode for the load instruction in the Scott CPU. The first bit has to be 0 because this is not an ALU instruction, and the other 3 bits, so the second to the fourth bits, are at 0 because this is a load instruction. The other 4 bits of the instruction are dedicated to the registers. So the register B, we can choose the register 1 and the register 2 as register B. So register A is 1 and register B is 2. And this means load R1, R2. So load the content of the RAM into R2, being the address in R1. So as a first thing, we have to choose an address where we want to put the instruction. We choose the address 0, so the cell 0. So we put this byte on the bus, and we acquire it in the instruction address register. In this way, this register point the next instruction, and we put this address in the memory address register. So we select the cell 0 in the RAM. Then we put here the instruction. So first 4 bits are at 0. So here is register A is register 1, and register B is register 2. So we put this instruction inside the cell 0. We have already selected the cell 0 in the MAR. So we give a set pulse to the RAM, and we acquire this instruction into the cell 0. So we free the bus. Then we have to put the address in register A, so in register 1. So for example, the address is the address 3, so the cell 3 of the RAM. We put this in register 1, given a set pulse, we acquire the byte from the bus, and we put this cell 3 in the MAR. So in this way, the RAM point to the cell 3, and we choose to put inside the cell 3 of the RAM like this byte here, a big byte here. We put this on the bus, and we acquire it into the RAM. So in the cell 3, there is this big, huge number, no? Okay. So now we have put into the cell 3 this big number, and we want to take this number from the RAM and put it in the cell in the register 2. So let's see what there is in register 2. There is the byte all at 1, and we expect at the end of the simulation to find in R2 the byte with the first 2 bits at 1 and the other at 0 we have put into the cell 3. If our simulation goes well, we have to find this byte into register 2, because we are running a load simulation, and we have to find into the IAR the number 1, because we have put here the address 0, and in the fetching phase we have to increment the instruction address register by 1 in order to put the next instruction, in order to point the next instruction. So we can run this simulation. I use my stepper cycle to just give a cycle, to run just a cycle, because in this way we are sure we run just an instruction. So I give a reset pulse here, and you see there is a cycle proceeding here. Now we go to see if the simulation went well. So we want to find inside the register 2 the byte we have put inside the RAM at cell 3. So let's see, and this is the byte we have put inside RAM cell 3. And also we have to see that inside the instruction address register there is the address 1, because this should be the next instruction. And here you see the address 1. So this is a load instruction, and we have loaded the data from the RAM to the register R2. This went well. Now let's see a store simulation. So, for example, the store instruction is this. This is 0001, which is the opcode of the store instruction is code CPU, and we use as a register A the register 1 and as a register B the register 2. So this is store R1, R2, which means store the content of R2 into the RAM address in R1. So as we have done before, we can put this instruction in the cell 0 of the RAM. We put this address in the instruction address register in order to point the cell, the RAM cell where there is the instruction, and we put the memory address register to point cell 0. So now we put the instruction into cell 0. So the store instruction, our store instruction is this. We put this instruction in the bus and we acquire it into the cell 0. We store it into the cell 0, giving a set pulse to the RAM. Okay. Now we want to put something in register 2 because this register 2 contains the byte which we want to store in the RAM. So, for example, we store as before this huge byte and we put it into register 2. Okay. Now we should put into register 1 the address of the RAM cell where we want to store our byte contained into register R2. So into register R1 we should put, for example, the address of the cell 3. So cell address 3, we give a set pulse in R1 and we acquire the address 3 into register R1. So for example, we want to see what there is inside the cell 3 in the RAM. We free the bus. Let's see what there is into cell 3. There is a byte all at 1. So if the simulation goes well, we should find into the cell 3 the content of R2. So this number here, we should find it into the cell 3. Now there is the byte all at 1. So our store simulation wants to store the content of R2 into the cell 3 of the RAM. Let's see if everything function and goes well. So we give through the stepper cycle, we run just a cycle. Okay, and then our circuit stops and we see what there is into the RAM cell 3. So we put the address 3 into the memory address register. We free the bus and we see what there is inside the cell 3. And there is the number which is also in R2. So let's see if this number is the same of that into R2. We give an enable pulse to R2 and we put the byte on the bus, and this is the same byte. So the store instruction worked well because we have been able to store the content of R2 into the cell 3 of the RAM. We also can check if the instruction address register has been updated and incremented by 1. So the address we have put here was 0, the address 0, and we should find now the address 1 if the fetch. Oh, sorry. Now I put the set pulse here, so I acquired this 111. So I cancel the content of this instruction address register that should have been at 1. So we can check this now, but the store instruction we have seen worked well.
Please leave me a comment, let me know if you liked this video, make sure you put a thumb up, click the notification bell and subscribe to my channel.